Greetings, everyone, and thank you for joining us today for another installment of the AI webinar series co-hosted by Maine AI Initiative and IEEE, a Maine Joint Computer Societies and Communication Societies chapter. I'm Julia Upton, Associate Professor of Mathematics at Husson University and Chair of IEEE Maine Joint Chapter. Our topic today is the current state of AI-powered math information retrieval. So the status quo, the challenges, and the open problems in this domain. Please type in your questions as they arise in Q&A, and we'll answer as many of them as we can at the end of the talk. And it is my pleasure to introduce our speaker today, is Dr. Behrooz Mansouri, who is the director of the Artificial Intelligence and Information Retrieval Lab at the University of Southern Maine DBX Center. He is the assistant professor of computer science at the University of Southern Maine, and he earned his PhD in computer science in 2022 with his dissertation on improved math information retrieval. As a PhD student at Rochester Institute of Technology, he has introduced math search models such as Tangent CFT and Math AMR. He also co-organized the ARQ Math Lab at CLEF 2020-2022. His current research is mainly focused on conversational math search systems. His other research topics include cloud detection and satellite images, chemistry question answering, and legal keyword extraction. So thank you, Professor Behrooz, for presenting today, and the stage is yours. Again, a little reminder, as you have questions, please type them in Q&A. The stage is yours, Behrooz.
All right. Thank you, Julia, for the introduction. And hello, everyone. I am Behrooz Mansouri, and my talk today is about math information retrieval, what we have and what we need. So before I start the talk, because I joined University of Southern Maine in fall 2020, so I just have one brief slide for introducing myself. So I'm assistant professor of computer science. I joined USM in fall 2020. I'm also the director of the graduate program in our department. And I'm also the director of artificial intelligence and information retrieval lab, AIR lab at the DBX Center. So mostly my current research is around math search. We have different topics, and I'm hoping today I introduce some of them to you, things like conversational math search, detecting ambiguity math searches, math image search, or math data augmentation. But also in my lab, students works on other topics, things like legal keyword extraction, and things that are also related to math information retrieval, like chemistry question answering. And then also we have set of other topics like cloud detection in satellite images. So let's go back to our main topic, math information retrieval. The first question is, what is math information retrieval? So similar to any traditional information retrieval system, and information retrieval system, they're just simply search engines. So we have a user, and the user has some information need. In math information retrieval, this information need is about some mathematical concept. So here we have a user that his information need is about finding the value for this limit. So users have information need in their mind. Now they want to use an information retrieval system. There are different ways that they can express their information need. And in case of math information retrieval, we have these three main categories. They can just simply write in their formula. Hopefully, if the search system support entries for formulas, so they can have isolated formula. We would call this a formula query. They can use ad hoc query, combination of text and formula together, or they can type in a full math question. So usually they use community question answering website or CQA, and they will write down a full math questions. And after they have expressed their information need, they are hoping to find relevant information to their information need. So in this case here, we can retrieve and return this post here. And in case of formula queries, usually system aims to return a relevant formula inside a document for the user. So this is mostly what we know as task of math information retrieval. User has an information need about mathematical concept. They will express it through one of these means, and the goal is to find relevant information for them. And here is an example of the system that we have for math information retrieval, a Scholar Fee. This was developed at the University of Berkeley. And mostly we view this as a reading tool that will support technical document and will support math. It has different capabilities, and here is one of them, declutter, that I really like it a lot. Inside a paper, you can select a formula like this one, and then you can see where else this formula appeared in the paper. So if you see a formula, maybe you want to refer back to its definition or see what are the other application of that formula. With declutter, you can do that. It would actually highlight the sentence in which the formula has appeared too. So this is one example system, very helpful tool for reading and understanding math inside the paper. Here is another system called MathDeck. The power of MathDeck is on its different means of entering formula. So probably by now you have this question in your head: how do we enter formula in a search engine? Mostly it's what I refer to as LaTeX. Some people call it LaTeX. You can write it as a LaTeX formula. But MathDex also provide this tool that you can draw a formula, and then they will use recognition methods to convert it to the LaTeX representation. They also have these keyboards that you can select, and will be like a view of keyboard with different math symbols that you can use to write down your formula. Now, why math information retrieval is unique and we try to have a specific method of searching compared to general searches? So this is a study that I did early during my PhD program, and it was on query logs of general search engines. So with query logs, they're very great resource for us to understand how people behave when it comes to a specific topic. And what we did, we take out query logs of a general search engine, we filtered the queries and extracted math queries, and then we studied them. So here are some interesting observations that we had. Around 80% of math queries, they were unique. They were not repeated before. So when we are developing math search system, we should be aware that there might be some unique information needs and queries that are not seen in the collection. So usually in our field, we have this issue of unseen data that we need to handle. And in math, that is one of the cases that we should be aware of. Our next observation was math queries are very long. So probably, you know, these days, majority of large language models, their competition is mostly about how much of context length they can support. And in math, what we saw for small queries, it was a general search system. The length of math queries, they were twice higher than general searches. And even more interesting observation was 20% of these math queries, they were in question format. And again, in our field, we have this task of question answering. So when developing math search system, one of the things that we should be aware of is our system should support answering math question. And you can see, again, this is way higher than what we have in general queries. But what is the broader view? Math information retrieval is a subcategory of a very well-known problem in information retrieval referred to as multimodal information retrieval. So we have a user. Let's for now consider that their input is text, but our collection is mix of data. It's not just the text data, It can be images, videos, table, diagrams, things like audio. And based on this input text, we want to find relevant sources, relevant documents. And by document, just don't mean the text document. It can be image or video or other formats. And sometimes the input query itself can have different modalities. It can be combination of text and a formula in our cases, which is two modality, and we should take care of that. And approaches that are currently being applied is maybe we can do individual searches, let's say one for formulas, one for text, and then combine the result of these searches, or find a unified framework or unified, maybe a better word is unified representation that you can pass in a formula and a text that will be mapped in a unique space. And then in that unified space, do your search. And these are the common approaches that we have for multimodal information retrieval. They are also applied for math information retrieval. But the question is, I show you that formula are represented with latex string, but in reality, that's not what we are using. We are taking that latex string and we are getting tree representation for this formula because it will give us more information about the formula. If we want to use just the latex string, that's a linear representation of formula, it will not give us too much of information about that formula. And tree representations are what we are actually using, and that's why we have multimodalities in math information retrieval. We have text, which is linear, and then we have formulas, usually represented as trees. And here's one of the most common trees that we use, known as symbol layout tree. Let's consider this formula here, x minus y squared equal to 0. In this tree, the elements in the formula are our nodes, and then these edge labels, they're showing the spatial relationship among these elements. Minus is located next to x, that's why we have n representing next. Y is located next to minus, but number 2 is located above y, so we will have edge label A here showing above. So this is one representation, and as you can see, these two representations are telling us about the spatial relationship among the elements, not that much about the syntax or semantic of the formula. And therefore, we have another representation called operator trees. Probably this representation is familiar to you from courses like compiler. So again, we have we have the elements of the formula as our nodes. So we have equal, minus, and 0. The edge labels here are showing the orders in which the operands should be executed. So for unordered operators like equal, for which the order of operands is not important, we will have the same edge labels. They're both 0 here. But for operator like minus or power, that the order of operands are important, we will have set of edge labels telling us that the order is important, and this is how we should consider the operands. So we have these two common tree representations that are used to consider formulas in our collection of documents. And then we have applied what we refer to as unification. So in this example, we have x minus y squared equal to 0. What if instead of this x, we had, let's say, a, b, or another variable? So we have this unified representation. It can be applied to both symbol layout tree and operator tree. I'm just showing you an example for operator tree. And these elements here are telling us what type do we have in these nodes. So for equal, because it's an unordered operator, we will have U. For minus, we are just having operator. For variables, we will have V. For numbers, we will have N. So with this unified representation that we are ignoring the values and paying more attention to the type, maybe that can help us retrieving formulas that are relevant but not exact matches. So later, if I have a minus b squared equal to 0, I can find similarity between these two trees. So we saw so far what the task is, what is the challenge. So we have the trees and the text. But let's now look at the tasks that we have and what test collections are available. In any information retrieval task, these are the three main things that we need to build a test collection. So the goal is we want to develop a set of systems and we want to evaluate them, seeing how good they are. To do that, we need topics. So we need set of queries, things that people type in search engines. So in the lab setting, we have to create set of input samples for the search system to be evaluated, and we call them topic. We are trying to mimic user who would write down queries. So we will create set of queries there. And then the search system, they will use this to test their output and doing the search over the collection. So as I mentioned, the other thing that we need is a collection. So after we have these input topics, where is it that we are doing the search on? So we have to provide a collection of documents. Now the system will take in the topics, they will return set of results from the collection. We need to know how good are these results. So we need relevance judgment set. So these are the three main components of test collection in information retrieval. And for math, we have different test collection. We had NTCIR collection from NTCIR 10 to 12, but one of the issues that we had there was the problem of math information retrieval was quite new. And in NTCIR collection, it was mostly the development of idea and the need for math test collections, and the size of data sets were quite small. So during my PhD, we organized 3 years of lab called ARQ or ARC Math Labs. And in each year, we develop a test collection. And overall, we call these ARC Math Test Collection. And in the next slide, I will explain what this collection is. So the task that we have in ArcMath, the main task or task 1 is called answer retrieval. The goal is to find relevant answer to math questions. So we have math question as the input to the system. These math questions, they're coming from Math Stack Exchange, where for question we have a title, we have a body, and as you can see, the body has text and formula in it. And as organizer, we try to consider diverse pool of questions. So we annotate them based on their complexity. What is the question about? Is in this example, it's about some mathematical concept. To answer this question, should we take care of both formula and text, or is it just the formula that we can pay attention to? So we have this tag. In order to answer it, are we dependent on formula, text, or both? And we had this last tag telling us if there are multiple parts to the question. So this would add more challenge to systems because they have to answer both parts of the question. So as the input to this system in this task, we are considering new questions. So question from 2009, then 2020 and 2021. That's how we separated the question in each year of our lab. So they have these questions as the input and they have to find the answer for them. But what are these answers? What we did was we collected all the answers given to what we refer to as old questions that were posted from 2010 to 2018. So there is a new question, let's say from 2019. The goal is to search over the answer given to the old question and find relevant ones, probably in your ranking, give them a high rank, and ignore or give low ranks to non-relevant answer. This is the task that we have known as answer retrieval. This is the main task. Probably you're asking yourself this question, wait, we have a new question and we're searching over old answer. How do we know that there is relevant answer there? They're given to some other question. So what we did here on a Stack Exchange, we have something known as duplicate question. We know that there could be some question here in these years that they have a similar or duplicate one in the previous years. And then for them, we have set of answers that might be relevant to this question. And this is how we build these question sets for our queries. We had another task known as contextualized formula search. So formula search itself is where the input for the system is just a formula. We want to find a set of relevant formula for it. For contextualized formula, again, the input is a formula and the goal is to find relevant formula inside post. But the difference is we need to take care of context. So the way to understand the problem of contextualized formula search is consider yourself reading this post. So you have a context, your goal is to answer this question. So you have a context, and while reading this post, you will see a formula here, and you just don't know what this formula is. You have some context, you have some goal to answer this question. So you want to find relevant information for this formula, but in this context. So the goal is to find relevant formula, give them high rank. Again, you should make sure you're considering the same context and ignore the non-relevant formulas or give them low ranks. And overall, how we organize these labs, not just for math, for any type of labs that you want to create in future. So in ArcMath, we had 3 years of lab. We have these 3 main steps. As organizer, we will introduce what are the tasks. We will provide them the data, like the topic, the test queries. We should also provide some training samples for them. But the issue is when we introduce the task and when we release the test set, we don't know the result. So we don't know which of these systems are doing well. We just release the test data. We will ask the participants to go run your model, bring your result. So in the second step, that's what the participant will do, not the organizer. They will train their models by any way that they want. They will use this test set and they will create their result. After they have the result are passed to the organizer, and then through what we refer to as pooling techniques, you can view pooling as a way of selecting good samples that you want to spend your energy and money on and hire assessors so that they read and they annotate the relevance of those. In case of ArcMath, so we release this topic, these math questions, they train the model, they return the set of answers for us. And what we had to do is select set of answers and pair them with the question. Then we train assessors, and in our case, they were math students. We trained them, we told them what relevance mean in our context, and then they had this interface that they were question and answer, and they had to judge their relevance. In ArcMath, we had 4 relevance degree of high, medium, low, and non-relevant. After this part is done, now we have set of relevance judgment, and we will evaluate using some evaluation metric in information retrieval. In our case, it was NDCG. And we will evaluate these systems, we will release the data, and we will publish the result. Now, knowing what the tasks are, let's look at formula search task and the approaches that are currently used for this. So again, as a reminder, this is the task that we have. We have an input formula. The goal is to find relevant formula for it and ignore the non-relevant one. In the case of contextualized formula search, we want to take care of context and make sure both the retrieve instance and the query, they are on same context. In early days of formula search, people were trying to just deploy what we have as traditional information retrieval models, we have text and we are doing text matching. And they were just simply using the latex strings to do the matching, considered as a term, as a word, and do the matching. So compare A plus B against A minus B. We also had these approaches of tuple sequence. So these approaches, they usually take the tree, they use some sort of traverse, like depth first traverse, they linearize the tree. And again, we have the sequence, so we can apply the traditional text retrieval models on them. Because we're losing the structure of the tree and we are not looking at the semantic as we had in operator tree, these methods are now forgotten. They were not that efficient. Then we have tree matching method. Some of these models, they just use symbol layout tree, some use operator tree, and some use combination of both. And now that we have tree, probably in algorithm courses, we have seen different ways of matching the tree. So we have sub-tree matching, full tree matching, for example, using tree edit distance, or doing path matching to do the tree matching and find the relevant form. And recently, mostly what we are doing are embedding models. So consider embedding models as if you take the formula through a model, you will map it somewhere in the space. And usually what we will do after we get the vector representation of the formula, we will use cosine similarity to find the similarity between the formula. So back to our example, A plus B and A minus B, they will be both mapped to somewhere in the space. We have the vector representation, we can use cosine similarity to find relevance. So majority of the work that we had previously for formula search, as you can see in these examples, they're comparing formulas in isolated against each other. But in ArcMath, we had this observation. So this was our input query, and some system retrieved this example as a relevant formula, but our assessor considered this formula, this retrieve instance, to be completely non-relevant to the formula that we have here. And they said, you know, the contexts are not the same. Here we have set of criteria on the retrieve formula, and they don't exist in the general formula. So mostly approaches that we have for formula search, they did not consider context. They were just doing the tree matching, hoping that the context will be similar. To solve this issue, an old idea in text mining and NLP was revisited, known as abstract meaning representation. So formulas in text are usually represented by symbol layout trees like latex representation. And then we have operator trees, which are somehow capturing the syntax and semantic of formula. We have the elements and their order on the edge labels. So operator tree seems to be capturing semantic, but text is linear. We don't probably have such a thing that captures some semantic of the text with trees. Some might consider things like syntax tree, but they're not actually capturing something like subject and their actions compared to things that we have in operator trees, that with these edge labels, we can see the order of operands. While we cannot use things like syntax tree, we have another representation known as abstract meaning representation. I personally am a big fan of abstract meaning representation. Right now, I'm writing a survey on it. I think it's a very powerful representation that is not appreciated as it should be. But with abstract meaning representation, or AMRs, and the idea is very old. The first time it was used in nitrogen system, but the time that it was revisited again was 2013. We have directed acyclic graph that can tell us who is doing what to whom. So what we have in our nodes, they are the core concepts, and with edges, we can capture the semantic relationship among them, which is quite similar to what we have as operator tree in math. Let's look at this example here. So we have the sentence, I saw Joe's dog, which was running in the garden. For this, we have AMR parser, so you can pass the input text and get the AMR tree. But if we look at this AMR tree, let's just consider the first level, C. So it's telling you what is the main message. Apparently someone saw something. If you consider just the first and second level, you will get the main message. I see a dog, or I saw a dog. Now you want more information, you can go down in the tree. What was the dog doing? It was running. What was the location? In the garden. Who possessed that dog? It was a person, and we had the name. It was Joe. And if you can see here, we have operator 1 because it's just the first name. If we had a last name for this person, we can have edge labels operator 2. So these edge labels here are showing the semantic relationships. So we have the act of seeing, the subject is shown with arc1, the object is shown with arc0 here for the subject and arc1 for the objects. So we have AMR quite similar to operator trees. And now we can probably propose an approach to unify text and math into one representation. So this is a research that I did in like the last days of my PhD program, introducing a notation called as math AMR. Let's consider this text here that has both text in it and a formula. Find a formula general solution. To create math AMR, what I did, I replaced the formula with some identifier. I call it EQ and an ID. These are ArcMath IDs. So in ArcMath, each formula has a unique ID. So for my text, I replaced the formula with some unique ID. I passed it through an AMR parser, and I got this tree here. And I knew where my formula should be. So now I have this AMR representation. For my formulas, I already have the operator trees. And all I have to do right now is take this tree from its root and replace it with what I have here as a placeholder for my formula. And now I have a unified representation of both math and text. So mostly in this research, we just introduce one notation of tree that can capture both text and formula. And then the next stages are to study how we can actually use this for search. I did some primary study. So I was using tree matching. We had some promising results, but I think we need to study this more, probably use a better tree approaching to use these math AMRs. Now, going back to answer retrieval task for math questions. So again, this was the task. We have a math question. The goal is to find relevant answer to this math question and ignore the non-relevant answers. There are two common approaches that have been applied to this problem. The first one are those that I refer to as traditional information retrieval models. They're mostly around combining result of formula and text search in systems like approach 0. So they have unique way of doing the search for formula, another unique way of doing text matching, combining the result. And we have systems like MathBrowser. They're still a fan of linearizing the formula and then treat the whole thing as text retrieval models. And recently, with all these BERT-based models, these are the current approaches that we have using models like SentenceBERT, Albert, or BERT itself, fine-tune them with set of training data that we had for math and get the result. And currently, still these systems are providing better results compared to BERT-based. And that's mostly around the reason that we are not fine-tuning these models well, and these models probably don't have enough knowledge about handling math formulas. So just going through the details of what we have as SentenceBERT for math search, and this is the search model that is used in the search engine called MathMix. I will introduce MathMix to you in the next slide. But For sentence bird, we usually have these two-stage retrieval, one using bioencoder and one using cross-encoder. So usually bioencoders, they can provide you some approximate matches, but they are not really strong systems. So they're used as first stage retrieval, finding set of candidates for you. And in some of the researchers, instead of using bioencoders, they just use BM25, which is a traditional retrieval model, but again, very strong for selecting candidate. And then we have the second stage. So select set of candidate, and with cross encoders, we rank them. And the reason that we have these two stages is cross encoders, they're not really fast. If you want to search over the whole collection, it will take you a long time. And search system, they should return results very fast. So that's usually what people do. They use one stage to select set of candidates, and then they use things like cross encoders to what we refer to as re-ranking stage. Now, in this system, MathMix, that I will introduce in the next slide, currently we're just doing the search with bioencoder, and the reason is our study showed it's providing better effectiveness. So MathMix is a search system that we developed in our lab, and it is an online system, so you can try it on mathmix.com. The goal of this system at the moment is to search over definition of mathematical concepts. So we have collection of data from archive where people can put their papers, from community question answering website on math, like Math Stack Exchange or Math Overflow. We have Wikipedia. We have math YouTube videos and math images. For our interface, we are using something that was already developed, MathLive, that support both formula entries and text. We also have a set of features like you can select what resource or what source you want to do the search on. We have some logging features that can be used in future research. And to have this model, this is what we did. We use Cybert model. We trained a model that can extract definition from text. And then having this model, we pass all the sentences in these collections through this model, and we extracted the sentences that contain some math definition in them. And as I mentioned, as our search model, we have bioencoder system. So a user will type in this query here, and then we will get its vector representation. All these contexts that we have from our collection, they are also encoded with the same model. Once we have the query, we will get this vector representation. We have the vectors here, and we are using KNN search to find relevant answers. Now, so far we saw the existing and type of things that has been done for math search, but there are many ongoing research about this domain and this topic. And in the next slide, I will briefly introduce these topics to you. So I want to quote LeCun for this, and I really like this tweet. And I think that's a major thing with research these days, that we're just stacking transformers on top of each other, throwing more data, getting better result, without actually caring about what these models are learning. And that's the main issue that we currently have with math information retrieval. We don't know how good these models can understand math, how good they can understand the concepts that we have inside the formula. How can they relate different parts of a math question together? And so far, what has been done in math information retrieval domain, we are just taking math data, we're throwing them at transformer model, we're getting result. But there are some initial study being done about how these models are learning math and how should we pass math data to these models so that they can understand it. So it's both based on the question that we have is how should we pass the data and how are these models learning math? Still, this is the big question that we don't know certain answer to it. Now, as you saw so far, The search system that we have for math and formula search, they're developed as a traditional search system. So someone will type in a query, they will get the result. But I highly believe that things like formula search, we need a conversation there. Math is not easy to understand. Ambiguity is part of math, it's part of formula notation. So conversational formula search, this is actually what a type of research that we are doing in my lab. So imagine this scenario when a user type in a formula. So we can have a bot trying to disambiguate this. So this is very general. This is just a formula. What is it that you're looking for this formula? And then the user said definition, and probably we can provide better answer that answer the user's information need. Another thing is about how do we ask this clarifying question? So we did this study last year with one of my grad students, and we used Math Stack Exchange to go through set of questions. And for question in Math Stack Exchange, we have a part known as comments that other user can comment on the question as clarifying questions. So here is an example. Someone posted a question with a certain title, with a certain body at some time. Later, someone asked a clarifying question and got a response to that clarifying question. And then the user went back and edited both the title and the body. And once that happened, someone was able to answer the question. So again, it goes back to this question that we have ambiguity in math information retrieval systems. And how are we going to solve them? We need clarifying question, but we don't have enough information about how to write this clarifying question and how to use them. So this is another ongoing research for math information retrieval. Math image search is another topic that we are exploring right now. The search system that we have right now support image search, but this is again another interesting problem known as text to image search, and specifically for math, how should we do it? So the task is, if I pass a text query, in our case a math text query, how can we find relevant images to that? This is one task. We also have the other way around. What if I pass an image and I'm looking for its relevant text? Or what if I pass a text, I pass an image and I want you to create a caption for that? And the bigger problem that I'm hoping in future I explore this after visiting these stages is, how can we pass an image related to mathematical concepts? There are some questions in the image and we can answer it directly without the need for any text. Consider a sphere and there's a question mark about its area in that image. So math image question answering is another thing that we are looking at. And currently, the model that we are using in our system is CLEAP. We didn't apply any fine tuning, but we are using thresholding. So when we are doing this search, we are considering certain threshold to return relevant images. One other interesting topic that we are working on is cross-language math information retrieval. So mostly what we have as online resources, they are in English, things like Math Stack Exchange. And we have a problem in information retrieval known as cross-language information retrieval. And in this case, so we have a query in different language. The user can pass that, we can process it, translate it in our target language, maybe in English, and then we will search through our collection. We will return a set of relevant result. We can translate it back to the target language or just return it as it was. As in our example here, after we, let's say, consider a Chinese math query, we can pass it through the translation system, do the search in English. We can just return the English, or the system can also do the translation and return the Chinese version of this. This is one way of doing cross-language information retrieval. There are different models that can be applied, but currently this is what we are working on as the first research on cross-language math information retrieval. Again, this topic is brand new, never touched before. And the last thing to mention is this study that we recently did. We just submitted the paper. We are in the era of large language models. It's a concern for everyone. And majority of the works that we have with large language models, they have a section on their paper telling how good their system is working on answering math questions. In this research, we were trying to see how we can use these models for math search, not math question answering directly, but can they be used for math search? We used two models, Llama 2 and Orca 2. The first reason, well, they're open source, we didn't have to pay for them, but also this model Orca 2 is a very good model in explaining their answers. And its base model was Llama. So we tried to take out Llama, put it next to Orca 2, and do our experiments. Here are the results on two of the experiments. The first experiment that we did, one of the challenges in ArcMath was we had to hire a set of people to do the assessment for us. We try to see if these large language models can do the assessment. If I pass a question and answer, can they assess relevance? Can they tell us if they're highly relevant, low, medium, or non-relevant? And these models, they fail to do that. So in assessment or annotation task between a math question and a math answer, these models were not that helpful. But for task of data augmentation, we asked these models to generate answers for math questions. And then we use these generated answers with their questions to fine-tune a model for math search. So we compare that with ArcMath data, with what Llama 2 and Orca 2 generated. And here we can see models like Orca that was fine-tuned on math data. Its promising result was on math. They can be as helpful as what we had in ArcMath. So this is again an ongoing study of how good large language models are for math. And one of the observations that we have, I think it's useful to mention this, is they are doing what we refer to as surface learning. Some of the results that are generated by these language models to answer math questions, at the first glance, you might think they're very good. When you read it, it would make sense, but they usually fail to give you the final answers. So still a room for improvement, even though that the steps that they are having for problem solving are good, but the final answers are not that promising. All right, so overall, what we saw was what is math? Information retrieval problem, simply information retrieval where information need is about math. These are the main tasks that we have in math information retrieval. Formula search, for which we have different models like embedding models, tree matching like tree edit distance, and there are attempts to using unified representations. And we have the task of answer retrieval for math question. We have two approaches using deep neural networks or combining text and formula searches. And you saw different ongoing topics, things like conversational math search, image search, multilingual search, and the use of large language model for math search. All right, I think that was all for me. Thank you for your attention.
Oh, thank you very much, Dr. Mansouri, for an excellent presentation. So we have two questions from the audience so far. The first one, do you have any examples where this process produces unexpected results?
By the process, is it the retrieval process?
I would assume it's the retrieval, yes.
So back to our example that we had here for both formula search and text search. So these were actually what some of these systems return as a relevant answer. So the way that we did these annotations, we selected potential answers. And these potential answers were actually the top K result returned by set of systems. And then we did the assessments. And you can see there was a system that thought maybe this answer is quite relevant to this one, but our assessor, based on the definitions that they had, they considered this to be completely non-relevant.
All right, thank you. Second question, this reminds me of work I was familiar with long ago in technology mapping in logic synthesis finding technology gates that implement portions of a logic network. A key issue there was common sub-expression identification. This seems important in math search as well. Do you identify and use common sub-expressions? For example, search on DAGs, not trees.
Yes, that's actually one of the main approaches that we have for tree matching. So we have models like tree edit distance that consider the whole tree when they're doing the matching. They're very strict. So we have this issue that it's highly possible that you miss some of the relevant formulas when you are doing the search. And that's why we actually apply sub-expression matching mostly on the trees, and it's similar like sub-tree matching. So we consider part of the tree and see how much these subtrees are similar. That's one way. And then we have path matching models that they see how many of the paths are similar among the two trees. But that's completely valid point. Doing the full tree matching is very strict. It can give you top K good result, but down in the list, many of the relevant instances will be missed if we just use full tree matching.
Thank you. See, I have a question regarding future directions for specifically conversational formula search. You mentioned that you attempted to use LLMs to provide relevance judgment, but the LLMs that you used were not quite efficient in providing such judgment, right, on the scale that you asked it to. Are you considering perhaps multiple AI agents to fine-tune the version of LLM system to provide relevance judgments?
Yeah, that's actually what we are doing right now. So this was actually, things are moving so fast these days. Just this morning before my talk, someone emailed me that the Orca that you have used, Orca 2 for this study, there is another version called Orca Math that was actually fine-tuned for math data. But again, in Orca 2, they promised that there was some fine-tuning on math. And one of the issues and what the current research on these large language models are not anymore on fine-tuning. It's mostly about instruction tuning and how we write instructions so these language models can provide us better result. And we have this result here, and we are redoing every experiment that we did before, because I believe we could have done it better if we had better instructions for doing this. I think there are rooms for improvement, definitely. We should try Orca Math and see how that would work. There are models there was another model called Lemma that they said it was just fine-tuned for math. The speed is high, we have to catch up with what we can, but definitely I think that's a valid point that we should consider.
So essentially what you just mentioned was prompt engineering, right? And so the set of instructions. Do you think it is possible to rely on AI agent to do prompt engineering to produce that optimal set of instructions?
That's a very interesting question. It would be like using AI on AI. So currently the research that we have on that, there was a data set developed for instruction fine-tuning. For me, I honestly don't think, at least in any time soon, we will be able to do that. Right now, majority of studies about the prompting and how we should do it. Using AI for that, I don't see that happening anytime soon, because our main challenge right now is on the prompts, and there are several studies being done there. I think as humans, we don't know how to do it so that we can train AI models to do that for us. So I think we need that study first ourselves to understand how prompts are working.
Well, perhaps AI can understand AI better than humans can. right, so let's see, any other questions from the audience? Don't see any. Right, well, thank you very much once again. Dr. Mansouri, it was an excellent presentation, very thought-provoking. Thank you very much. And thank you everybody for attending today. And have a great day.